This is the class number 21, recorded on October 22nd of 2019. So this class we're going to cover the planar frame structural analysis programming in Octave. We're going to start in the iPad showing the description of the problem we want to analyze, and then we're going to move to Octave to do all the programming, and I'm going to show you the architectures of the structural analysis program of the planar frame system. Okay, a nice and simple one. First, we should do more, of course, but for now, this building. Okay, so once we have the building, we will assign the node number, and it is up to you, for here up to me. So node number 1, I put it 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have the node number. We will have the element number and also the description for element. First of all, let me give you some idea. The building like this, a few story building, generally the size of the beam cross section should be somewhere around 20 by 40. The span here is 5 meters, so make it 40 by 50, 20 by 50. Whereas the column for 3 stories is gonna be 20 by 20 centimeters. Just the size, approximate size. Basically, when you start the analysis for your design of the building, you will have to estimate the size first, right? You don't know the size prior to the structural analysis. You got to conduct structural analysis first, and then get information about the internal forces, moments, and then you design the member to carry those internal forces, and then you get the dimension, and then you get the dimension. Your job is not done over there, because your dimension might not match with the assumed dimension, so you can rerun your structural analysis by putting the real dimensions from your design, right? Analyze again, and then you'll be able to get the new distribution, which is, well, it should be quite close to the original assumed dimensions, analysis from the assumed dimension, because if you have some experience, you will put quite make sense dimension in your analysis. So the ratio between the EI or the AA thing, okay, will be quite realistic from your assumption, which is well, from the experience. So basically, for the beam, you have the BH cube over 12, whereas the column, okay, the H is 20. So the ratio for the H cube to the 20 cube, right? 5 to 5, 25, and then you get 125 triple O. Over here, 8 and triple O. So what is the ratio? 125 to 8, right? 125 to 8 1, okay, and 4, around 15 times. So the EI you have from the column is just 1/16 of the EI you obtain from the beam. If you use the unit of the meter, well, you end up with the same thing, alright? But I just wrote the centimeters here first. When we put in the number, we will put everything in terms of meter. So you can calculate the EI. The E, we will use the same concrete for this whole building, so E will be the same. What is the E for concrete? About 20, yeah, 20 something, 20 GPa, gigapascal. For steel, it is about 200. Concrete is about 10 times, approximately. It's about 10 times less. So 20 gigapascal. Right. Everything will be in meters. So I change from 0.2 by 0.5 meter and 0.2 by 0.2 in a meter. We have beam, we have column. We will put the node number, element number. So I call this one number 1, number 2, number 3, number 4, 5 as a beam, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Right. We will come up with the information. First of all, structural analysis program just work the same way beam and truss, frame and truss. It doesn't really, they don't have a major difference. You still have to make a XY core, right? So the data structure for XY core, let me XY core will be like before. First column is the X, second column is the Y. And I think I shall give you the length information. So this is the span is 5 meters. This is also 5 meters. It will be fun at the end of the day. You can play with the different building. In fact, you can just design the commercial building or the shop house using the program like this. Good enough. You can do the 3D. It's not difficult at all. And once we're done with this, you realize that there's nothing in SAP but just a graphic user interface and some nice solving scheme for the linear solver. We can do pretty much all of that by hand, by our own program. 3 meters. Well, for the large structure, you have to rely on the graphic user interface. Large building, you cannot afford to just put element by element. So a program, structural analysis program that talks to the CAD program. Like AutoCAD, you get the floor plan from AutoCAD, import it, and then you get the grid lines and so on, and then you can construct the model quite easily. That's the price you pay majorly, right? Because you cannot do things by hand. To import from one architectural drawings to the structural analysis program. But the other things, the main engines, are what we learn in here. XY coordinate. So I give you just a rough idea. We don't need to go through in detail. So start with 0.0 and 0.0. This is the first node. Second node, 5.0 and 0.0. The third node, 10.0, 0.0, and then number 4, 0.0, and then 3.0, number 5, 5.0, and 3.0, so on so forth until the last node, number 12, which is 10 and 15. So you get this data structure, or 3.9, right? Oh, thank you. Oh, okay. So element number 1, node number 1, 2, 3, number 12. Okay, so you get this data structure, and not only just the XY core, you're gonna come up with another thing, which is the Nmap. Nmap, where could I put it? We'll put it somewhere. Load will be, we will talk about load later. Nmap. I think I should get the iPad Pro. And that's a rip off for me. So Nmap, start with element number 1. Well, that depends, right? If you want to, well, select whichever as a starting and whichever as the ending node. Okay, up to you. We're gonna put the integer there. So first one, 1, 4. Second element, you can do the 5, 2 if you want. Third one, 3, 6. You can try to confuse the computer. It will not get confused at all. But well, we can just shuffling things around to, okay, for fun. So 4, 5, 4, 5, and 6, 5. And on and on and on and on and on. We don't need to write everything down. To the last element, which is 11, 12. So that works in pretty much the same way as the truss member. So here we have element number 1, 2, 3, 4, all the way to 15. Okay. We have elastic modulus, we have cross section, we have end map. The next step, we need to look into the force, right? The application of the external force. So the external force will be around here. I will show the applied force in this picture. Well, as you know, this is the building. We expect the load, gravity load. So for second floor, third floor, you might have one load intensity. At the top, which is a roof, it might not be as high. So I put the different load there. That's the first thing. We need the load on the beam. I think it is somewhere around 4 metric ton per meter length. When you distribute the load from the slab, including the dead weight of the slab and also the live load from the area usage, that adds up to about, let's say 4 tons per meter length of the beam. 4 metric ton is 40 kilonewton, right? 40 kilonewton. So this is 40,000 Newton per meter. Likewise, for the third floor, 40,000 Newton per meter. Well, we assume that this case we have the slab on ground, so the first floor we don't have it. But just sort of, I don't know, should it be called the tips or not, but you can see that when you analyze the structure, you will apply some boundary condition there. You apply the boundary condition, the structure in the real construction never come back to you and talk to you asking, should I behave this way? Alright, it is your job to design everything such that it behave like the condition you posed in your analysis. So, for this case, if this is the model we have at the design, at the analysis phase, using the fixed support at the base like that, what will be the condition that you have to put in the in the design? Fixed support means it was restrained against all displacement. So the displacement in vertical direction, of course, if your pi is not fail, right, it will carry the load and it will restrain the vertical displacement. But not only that, you might also expect the horizontal movement. For this case, it is just a planar system, so it is the movement along the x direction. But along the x direction, if you give the condition, how do you pose this condition to your structure? Because in the reality, this is your foundation. Your foundation is sticking on the pi. It could be driven pi. The driven pi, the reinforcement inside the driven pi is generally just a pre-stressing strand. Because the pi was manufactured to carry the vertical gravity load. So the steel reinforcement is very low. Percentage of steel normal rebar is very low, unless you specify that you need this size to be put in the pi, and for this given length, you can order the pi company. Sometimes you design and you want the pi to be able to carry the moment. Sometimes you design the pi and the pi might not be cut below the ground. You might need the pi to just stick up above the ground. And you know, the pi is not designed to carry that moment. So pre-stressing inside the pi is just for the transportation purpose and for the piling procedures. Transportation, because you got to put the pi on the truck, and that is like, okay, that will be the recommended LO5 and LO5 from both ends, kind of thing like that, to minimize the bending moment you might have in the pi, to prevent from the cracking. But still you need the pre-stressing to always keep the concrete under compression. So that was the pre-stressing for just transportation. And okay, maybe for the piling, because you need to hammer the pi head. So when you hammer the pi head, you have the stress wave going through. So you have the compression wave and then tension wave, alright? So that is going to damage your pi. So pre-stressing also help in these two aspects. But it is not designed to carry the moment under the service condition. But if you want, for example, you do you install the pi to serve as the retaining wall along the canal. You don't want to drive the pi, cut the pi below the water level, and then make a foundation and then make the, oh, that's a lot of cost. So you can specify that inside the pi, not only just the pre-stressing strand will be there, you also need maybe 4 dB/16 to be installed over this length, 6 meters, 8 meters, over the range that you expect the large bending moment from your analysis. Okay, that could be done. But my main idea is that the pi is generally slender. The cross-section, because of the load carrying mechanism that we expect, is to be the axial load only. So if you want the axial load only, the cross-section of the pi, well, can just handle that axial load, alright? But axial load is the stiff mode of the member, but bending mode is the weak one. And again, it's not designed for that. So if you have the foundation like F1, F1 means just one pi, like this in the picture. Only F1, then the rotational rigidity is very, very small, very weak under rotation. Likewise, for the horizontal movement, the restraining effects provided by the pi is very small. Pi is slender. It can deform very easily. So in order to simulate the condition we use in the analysis procedures, we said that the support is a fixed support. But in reality, you don't need more than one pi. If you put 2 pi, yes, the rotation will be restrained because you have a force couple, right? But still the translation may not be fully restrained, but it is better than 1 pi. But in general, for small building, you need just 1 pi. And you don't utilize the full capacity of the pi, because you just need something to come down to the stratum level or the bedrock level to prevent the settlement, and that's it. In Thailand, we use like the pi. Sometimes the sizing is really large, like I-26 or square 26, because some area the soil, the soft clay thickness is somewhere around 24-25 meters. So the size smaller than 26 cannot be driven down because it's gonna buckle before it gets driven down. But the load, actually maybe I-18 is capable of carrying that axial load. The problem is about the insulation and so on and so forth. So you got to use the pi, and only 1 pi is just more than enough. So more than 1 pi, more than enough. Why do we put F2? Waste of money. So we put F1. When we put F1, then the pi head fixity seems to be out of our knowledge. We cannot guesstimate the horizontal stiffness of the foundation. We cannot gauge the rotational stiffness of the foundation. And then we assume the fixed condition. So now, how to come up with that perfect fixity? How? So that's why the ground beam is important. So nobody just stick the foundation like this, and then just go straight and then put the beam on the second floor without the ground beam. Because when it is analyzed, it is like this. Okay? So once you put the ground beam generally it is quite big. People actually are not afraid of the collapse of the first floor, because the most collapse could be like 30 centimeters, and then right? The soil below will take care of everything. But the ground beam is designed to be big in order to restrain the pi head, the foundation, against rotation and against relative displacement. When it is connected together throughout the building, that gives you rigidity to the foundation, and then your assumption on the fixity of the support, that it is a perfect fixed support, can be applied. The thing is that you analyze this way. When you design, you have to design and make sure that your structure behaves the same way as your structural analysis model. If you design the pin, make sure that it's gonna be the pin. Okay? So this is extremely important, and this is a part that many times the collapse or sort of failure is caused by this inconsistency between the structural analysis model, especially the condition like hinge or at the support, versus the real construction. You don't want moment here, but you put the fixed member there that restrain the moment, then you end up with trouble. Or sometimes you want that thing to resist the moment, but you just release the reinforcement, then you get into trouble, right? Make sure that everything is consistent. And now we have the load. Let's put the roof load. It could be reduced to just half of the other floor. So, okay, about 20,000 Newton per meter length, or 2 tons per meter. Thinner slab at the roof. I don't understand why people put the thinner slab on the roof just to save money, and then 15 years later you find the bad corrosion of the steel reinforcement at the bottom of the slab, of the roof slab, because it is thin, and you use maybe like a low quality concrete, low strength concrete. Sometimes you don't really need like a 380, 350 KSC or 3840 megapascal grade concrete. For general construction, you will need like 21, 24 MPa. That could be enough, right? But the point is that when you do the roof, well, you know the roof, it is not protected. It is exposed to the severe environment, thermal, shrinkage, and also some other thing like the water seepage. Okay, it is a durability point of view. So it rains, and most of the time the level is not perfect, so it traps the water. And most of the time the roof slab is thin because the design load is small, so the slab is thin. Slab is thin. What is the consequence? It sags. It sags. And as it sags, it makes the water pond, right? Something can grow. You can raise a bunch of mosquitoes there, right? You give birth to mosquitoes, well, whatever. The frogs can come in, and well, that's a zoo up above your roof. So it traps the water, and if your concrete is porous, water seeps down, then it comes to meet the steel reinforcement. Steel reinforcement get rusted. Maybe for the first few years, the carbonation is not there yet, so the pH is still very high, so it is difficult for the corrosion. But as the structure ages, so the structure is exposed to carbon dioxide, and then you have the carbonation penetration. So the pH drops. Steel reinforcement gets corroded. Rust comes in. When the rust comes in, then it expands. Concrete breaks out. You see the breaks out along the line of reinforcement. That's just nothing more than just the corrosion problem. And that's it. You got to fix. You got to remove and make a new roof and so on. So when you design, maybe you put the specification for the roof slab. I personally, if I construct my house, then I put like a high strength concrete there. High strength concrete, low permeability, low pore, because you don't have much excess water, right? From your mix. Well, it is difficult to pour, of course, more difficult, but what's wrong with that? It is just a slab, it is not a beam. It's not a column, so slump might be low, but it doesn't really matter. So lower slump, but more water. Well, you can vibrate and get it packed very nicely as it is a slab, easy to pour anyway, right? And then less permeability, that will make your slab more impervious to water. Well, if you want, you can put like the water blocking, like some sealant on top, but make sure that those sealants on roof sealants is not like forever. It does not last like 30 years without maintenance. Generally the sealants, roof sealant like this, 4 or 5 years the system fail, you need to rip off, and you can reapply the new coating, right? There is some sort of coating is called like the pore blocker. So that's some sort of that's a type that you can mix with some water solution. You spray on concrete, it seeps into the concrete, and then it forms the crystal in the pores inside concrete. You don't coat the top, you spray, let this solution seeps into the concrete material, and then it dries out, it forms the crystal, and that crystal blocks the waterway. So this is the blocking from the inside, and then you can try to block from the outside, which is the coating. The coating can be failed in every 5 years, but this blocking system is gonna last longer, okay? And pour concrete in the evening. That's the trick. So if you pour concrete for other floor, well, during the noon time, it dries out very quickly, especially during the winter. The winter month, weather is very dry, and you pour concrete in the morning, sunlight, full exposure to the heat and the dry weather. Evaporation is very fast, and for the slab, you know, the exposure area per volume is quite large compared to the beam, compared to column. So you will experience the plastic shrinkage a lot in the slab construction. So if you pour concrete during the daytime, like in the morning, well, concrete starts forming, turns into the plastic state after about 2 hours. Plastic state means, okay, it gets hardened, but it has no strength. So hardened, no strength, and then suffer from the shrinkage that causes the crack, right? And then you have all the cracks over your roof slab. The bigger the slab is, the more crack, because the more restraining effect, right? So if you do it in the evening time or maybe late afternoon time, you pour concrete, and then sunset, it's not too hot. If the weather is quite dry, then after the concrete gets hardened, you spray the water on the surface. In the first day, you need to spray a lot to make sure that concrete gains strength before it suffers from plastic shrinkage. And then you get a very nice roof slab, and that's gonna be long lasting. Okay, so don't be stingy with the thickness. The load is small, but you don't want the sag. If you have a sag, you have water pond. If you have water pond and concrete is porous, it seeps down, it destroys your reinforcement, and so on and so forth. For your house. But okay, I don't know, the market could be very competitive. These days somebody even use just the precast plank and then pour the topping 5 centimeters and then water just come down, right? And normally people sleep in the topmost floor, so you gotta sleep and then get the water drip down. Generally the case. Let's put the load for the if the area is, let's say, 5 meter by 5 meters, okay, 5 meter by 5 meter, 2 base, you have what? 50 square meter. 50 square meters, the dead load per square meter could be, well, let's say 400 kilogram per square meter. So that's 0.4 tons, right? 0.4 ton per square meter. You have 50 square meter, you have 20 ton in weight for the weight per floor, right? I just did the 0.5 concrete slab is somewhere around, like, if it is 15 centimeters, it is like 300 something, right? And then you average the weight of the beam and the column in. I think 0.4 does the job. It should be okay. Just rule of thumb number to come up with something realistic rather than just put 5-10 tons as a lateral load. Okay, so let's say 0.4 times the 50 square meters, then you get 20 metric tons for the weight of each floor. In general, for earthquake analysis, we apply the load at the floor level. Why? Because the column is insignificant. The concrete for the column compared to the floor is like 100 cubic meters when you pour one time. You pour a column is nothing, right? So as the column is insignificant, we lump all the load to the floor level. So 20 tons for each floor. And then what? The earthquake load, if we put like 3% of the weight of the structure, overall weight. 3%. Okay, so 20 tons divided by 100, you get 0.2, and then multiply by 3. Why is it so small? 3% of the weight. Yeah, it could be just that. So 3% of 20 ton is 0.6 ton. 0.6 ton, which is 6 kilonewton. So this one at the middle one could be 6,000 Newton. This one 4,000 Newton and 8,000 Newton. Okay, so let it vary. The rooftop suffer from the maximum. Okay. Okay, looks good. What else do you want? Do you want to apply some sort of settlement to the structure? We can do that if we want. Apply the, well, that will be when we enforce the boundary condition, right? The thing is that when we apply this load in your input on the Octave, you got to see here. For example, number 4 and number 5, element number 4 and number 5, number 4, 4, 5, number 5, 6, 5. This is 4, this is 5, this is 6. Number 4, 4, 5, start to ending goes like this. Number 5, 6, 5, start to ending goes like that. So, if start to ending goes like this, and this is your fixed end, this is your load. Okay? So, it is, when you compute your fixed end reaction, the WL over 2, WL over 2, WL square over 12, WL square over 12. These are the sign convention for the load coming down and the local coordinate pointing towards the right. Whereas the system there, as the local coordinate points towards the left, you got to well, turn upside down, because the positive sense of fixed end reactions, as the local coordinate goes like this, right? Positive goes like this, and then rotation, positive rotation goes like this. So, well, here is what you obtain as a fixed end reaction to this load, but then it is on the opposite direction to this positive sense. Or basically, if I just rotate this picture and then make it go like this, it's gonna look like the load coming this way. Right? If I turn my head upside down to see this picture, I find that I will see this. If I see this, generally we have the load coming downward. Now, this case, as we set up the local coordinate like this, you're gonna see the load coming upward. As the load coming like this, upward, your fixed end reaction will be in the opposite side. So the W we apply, this case here, 40k Newton. This case, minus 40k Newton. This is associated with the way we set up starting and ending node. Okay, so that depends on the program, but it does matter when you apply the local coordinate, when you apply the load on your member, which is in local or refer to local coordinate. The direction does matter. How you start, how you end the node does matter. The program will not understand you automatically, right? This is the protocol that we use to write the program. So be careful, right? But if the graphic user interface allow you to do the global coordinate load and the local coordinate load differently. Okay, for the global one, yes, you just follow the direction of X, the direction of Y, positive, negative, how the load align with these axes. But if you apply in local coordinates, then how it starts, where it ends, that does matter. The perception of the computer to your load. You can do this and just put 40 and plus 40 for the different setup of starting and ending node, for a different setup of the local coordinate, and you will see the different solution. Okay, and something like this, if you never write the program or see how the program is made, then you don't get what's going to be the problem that you confront. But it is algorithmic issue. So hope you have some concern like this. And the best thing when you're gonna use the program and you are not sure about how this thing behave in the program, just come back to the basic. Construct a very simple structural element that you understand the behavior quite very well. It could be a part of 40-story building that you are designing, but you don't really have to test the idea or test the module of the program or the input somewhere in that program that you are not so sure. Test it in that 40-story building, because the response is so complicated. It combines all the loads. Make something simple like cantilever beam, a cantilever column, or maybe just one bay frame, and then you know that if you apply load like this, it's gonna behave, it's gonna displace like this. You be able to perform the hand calculation to check. Maybe you perform Excel calculation to check if you get something that match with what we learned in the class. And if you don't get that from the program, find out what goes wrong. Maybe it doesn't go wrong, but it might not be going in the same way that you think. And if you cannot come across the issue in the simple model, never proceed to the complex model. Alright? Always come back. Okay, no matter, you go to the design office, that depends on what platform they purchase. SAP, Statpro, whatever, robot, you cannot choose. And when you come to the new platform, you might not understand the nature of that platform that well, right? So please check a little bit. If I were you, I will always check simple cases and make sure. I used to see some work. Analysis is done, apply the slab using the shell. You have the frame structure, the slab supposed to rest on the beam, right? Transfer the load to the column. Get the analysis result. I check, okay, how does the slab deform? Okay, slab deform. How about the beam? The beam doesn't deform. Things like this. If you don't check logically, look at your result and see the logic. See if that should be believed or not. If the slab goes but the beam doesn't go, that means the beam doesn't carry the load. And what's wrong with that? Maybe the node, the restraining, like the connectivities between the degree of freedom, vertical degree of freedom between slab and beam are not connected well. It could be the default of the program. If you don't make the link, it doesn't connect. It could be that way. It's not like you make the model of the building, make model, make slab, make beam, and the program will understand that this slab is going to move along with the beam. This is example. I show this example. I think it is very relevant to this class. When you design the slab or when you analyze the slab using the shell or the plate element, the nature of finite element, the more discretization, the better the result is. So the slab you discretize, make many shell elements like that. Whereas for the beam, you might not do that. You might just, okay, my beam is from here to there, and here is the column. And you make all this, and you understand that program will take care of everything for you. Program will understand that, hey, slab goes down, the beam has to go down along. Well, let's look at the logic. When you write structural analysis program, the degree of freedom are here, just these two ends. Whereas the node on the slab, on the shell, you have here, here, alright, x, y, z, x, y, z. If there is nothing that is used to restrain the profile of the beam to the degree of freedom of your slab, you don't connect the beam with the slab, right? And using the beam like this, the beam is discretized by having just 1 and 2 nodes. So you don't have the degree of freedom in between. Whereas for your plate, you have the DOF everywhere in between. But you don't have any on the beam, so how do you link these two? Turns out to be the issue. And once the analysis run, you complete it. Many people without the education on the basic for the structural analysis, just believe, oh, the program is smarter than me. I don't argue with the program because I don't think I can do better, which is a bad and wrong mindset. Because something like this happens, you need to check the program, you need to check the output, deform shape everywhere, you check it. Something like this happen, you come back and think, what goes wrong with my model? And if you look into it further, you find that you don't specify the degree of freedom along the beam. So if you want to stitch the beam to the slab, you might need to discretize your beam along, and then you might need to put the condition that link between these two. Okay, you may not need to put to link between the rotation of the beam to the slab. It might not be necessary because the slab rigidity might not be that significant in the bending compared to the beam. The beam is very stiff flexurally, right, in comparison with the slab. But the deformation should goes together. So you stitch the deformation, but you may not stitch the rotation. If you can stitch the rotation, well, fine. And then you run the second round of analysis, you might find that your beam and your slab goes together, and that makes perfect sense. Okay, now so we start in Octave. I just copy the function main that we use for the truss, and we're gonna modify this one and use for the frame structure. So again, the node, we have to input number of elements. We also have to input, and then we have the XY coordinate. Node number 3, 10. Node number 4, I think we can just do it this way. Okay. So we have 0, 5, 10, 0, 5, 10, but this will be 3, 3, 3, 6, 6, 6, right? And 9, 9, 9, 9. Delete. Okay. And then the node number will be changed to 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait, don't want that. And then what? Okay, now 0, 5, 10, 3, 6, 9. Then the mapping. So the mapping we use 1, 4, 5. Oops, 5, 2, 3, 6, 4, 5. What? Insert 4, 5, 6, 5. 6, 5, 6, 5, and then what? 4, 7. 4, 7. 5, 8, 8, 5. Fun. 8, 5, 6, 9. And then 8, 7, 9, 8. Mm, 7, 10. 7, 10, 8, 11. Okay. 9, 12. 10, 11, 11, 12. Close the bracket. Six, 7, 8, 8, 9, 10, 11. Hmm? 11. Okay. Okay. 12. I don't like this autofill. Is there any like editor show long line to edit navigation? Is that go to line next bookmark, select matching brace preference style preference? What is the preference? General command framework workspace variable editor shortcut workspace file browser no editor show line number, highlight, show horizontal. Should it be editor? Highlight all, long line marker, command, general, use system icon, show status bar, cursor blinking. Okay, fine, I cannot find still. Just annoying to like 15 element. Okay, done. We have nmapped structural element properties. Plot this structure. So let me just put a return here to stop the code over there. These properties I will just comment it out for time being, and then I will check the code, check the input. What main frame call from, okay, dummy. All right, I got to put some number. Okay, so this seems to be the structure we want. We continue. So element properties. What kind of properties? Oh, last time actually we didn't play with the temperature effect or creep, etc. If you can do, if you want, you can do. Yeah, we're gonna use this class opportunity to try that. Okay. Properties, we have thermal coefficients. We have, this is what the EA, right? That this is the EA for the truss. So here I think we're gonna have the E, we're gonna have the A, and we're gonna have the I value. All right, that makes more sense. So for the E, we have the 200 gigapascal. So that is the 2E. 100 giga means to the 11. All right. 2.0. Let's check. 2.0 E11. Okay, yeah, it understands this way. 2.E11 only. Yeah, the same thing. It will understand that this is the float. Oh, this is not steel. Okay, this is concrete. Okay, thank you. And then the cross-sectional area for element number 1, which is the column, is 0.2 by 0.2, which is 0.04. So you can make it 4.0 E minus 2. To avoid like too many. And the I, 0.2 times 0.2 cube. So you have 0.04 times 0.04, which is how many O? Okay. That is the 1.6 E minus 4, right? 0.2 and then divide by 12, right? So it is 1.333, 1.333 to the minus 4. 0.2 multiplied by 0.2 cube, you end up with 0.2 to the 4th. 0.2 to the 4th is 1.6 times 10 to the minus 4. And then you divide by 12, or we will have minus 5, right? 1.333 times minus 5. Minus 4 is from 0.1 to the power of 4. You get minus 4 first. Alright? 2. Oh, yeah. 4, yeah, correct. And thermal expansion still there, unchanged. Element number 2 is also the column. Element number 3 is also the column. Element number 4, what is that? The beam. We paste first. Number 4, number 5, number 6, 7, 8, 9, 10, 11, so we need a few more, right? 12, 13, 14, 15. 12, 13, 14, and 15. So 4 and 5, they are beams, and 0.2 times 0.5. Why do we need to calculate where we have octave here? 0.2 times 0.5 cube divided by 12. Format long. Okay, just that. Oh, 1, 2, 3. We'll keep just this many. Okay. 4 and 5. Okay. 6 column, 7, 8 column, 9 and 10 are beams. 9 and 10 are beams. 11, 12, 13 column, 14, 15 are beams. Okay. Now, you get the properties of each element. The cross-sectional area has to be changed as well, right? So the cross-section is 0.2 times 0.5. It is 0.1. Where is it? Okay, so this is the beam. The beam. And here. Okay. 44411, 44411, 44411. This plot, okay, we get the correct shape of the structure. Actually, this was supposed to be in the input file. That's what I don't like it, because every time you edit the geometry, then you edit the core program. You don't want to come here. The geometrical properties of the member, we can use this because to determine the orientation of the member, you don't need a special subroutine. So you go ahead with this one. We have essential boundary conditions at the DOF 1, 2, 3. So let me just one, two, three. Four, 5, 6. And 7, 8, 9. Okay, good. Easy. I copy this one, and so you can put the prescribed boundary condition to be something non-zero. It is possible. We get boundary condition. You don't need to do anything with NBCN because this gonna determine the size of the matrix automatically. Right? So just that, and then apply DOF forces. Okay, force at the degree of freedom. We have point force applied at 3 nodes. If you remember, and those 3 nodes are, well, 6, 9, and 12. For 6 and 9 and 12, the load was applied in the horizontal direction. So for the 6, at one node you have 3 DOF, X, Y, and rotation. The first one is the X. So 6 multiplied by 3, you get 18, and then minus 2, you get 16. Alright? For the 9 to 3, 27, and minus 2, 25. Degree of freedom number 25, and 12, 36 minus 2, you get 34. And we have the load. Load was applied to the right hand side, so it is positive sense of the X. What is the load magnitude? Start from 4,000, 6,000, and 8,000 Newton. Okay. The point is that let's take a look at the now we don't have anything to do with the degree of freedom yet. Plot structure. Okay. Nmap I2. Alright. For here, F6 is not going to be 2 times number of nodes. You will have 3 times number of nodes because each node carry 3 degree of freedom. And then the FRC, okay. Stiffness matrix again has to be 3, as you have 3 DOF. Next, you come to NELE loop, and this is truss stiffness. So I change to the frame FR stiff. FR stiff, I look up in here. Okay, I get truss stiffness, and then I do the save file as TR, turns out to be FR. Frame stiffness. We need the E, we need the A, we need the I, we need the length, and we need the orientation. That's all we have to come back and plug in over there. E, A, I, length, orientation. E, Okay, there. A, second column. And I. So for the E, first column, A, second, I, third column. Geometry 1, geometry 2, what are these? Geom 1, geom 2, or length and origin. Okay, fine. Or length and orientation. Okay, so we don't need to mess with that. The plugging in is gonna be 1, 2, 3. It's gonna be 1, 2, 3. Okay, this nested loop. Well. 1 to 2, 1 to 2, because you have two sets, but in here it is not 2 by 2, it is 3 by 3. The sub block contains well, we will come back to here. We finish this one first. Okay, one at a time. Okay. So K local is the 6 by 6, right? Local coordinate 6 by 6. So start with maybe we get these sets first. Yes, this could be useful for now. But it is 1, 1, it is 1, 4, it is 4, 1, and it is 4, 4, right? And then it is the E multiplied by A divided by length divided by K local itself. The other entries are for the bending, for the flexures, but the flexures we have not filled them in yet, so they are all 0. So we can multiply the 1 minus 1 minus 1 1 with the EA over L through the whole matrix, and then we come to the 2 2. I will leave this like this first. Oh, what? And then you have 4 repeating sets of this. Okay, so row number 2, row number 3, row number 5, and row number 6. And then what? 2 2 2 3 2 5 2 6 3 2 3 3 3 5 3 6 5 2 5 3 5 5 5 6 and 6 2 6 3 5 6. Okay, all right. And this is we'll call this one F12 equals to E times I 12.0 times 12 EI over length Q
F6 is equals to 6.0 times E times I over length square. F4 is equals to 4.0 times E times I over length, and F2 is equals to 2.0 times E times I over length. Okay, so it will be easy to put the F12 there. This one is F6. Next one is minus F12 and F6, F6, F4, F minus F6, and F2 minus F12 minus F6, F12 and minus F6, F6, F2 minus F6, and last one F4. Okay. Okay. Direction cosine is 6 by 6. Again, I never remember anything in the world. I got to go check. Direction cosine 1, 2, and then you have the 2, 1 and 2, 2, and direction cosine 3, 3, which is equals to 1.0, right? And then we're gonna copy that. So start with what? Cosine and minus sine, or the okay, I can check back to the class notes that we derived. So the transpose is no, not this one. This is the no. We need the direction cosine. Which one? Which one? Not this one. Long time ago. Just sine and cosine switching around that. Number 5, I guess. Lecture number 5. Where is it? Okay, number 5. Okay, there you go. Cosine, sine, and then minus sine and cosine. And then 4, 4, 4, 5, 5, 4, 5, 5, and 6, 6. Okay, got the direction cosine. Then the KELE is computed accordingly. We save it. Frame stiffness seems to work now. If you don't believe in this one, then let's try. So E, let's make the E something like 1. A equals to 1, I equals to 1, the length make it 1, and then make it 0. Okay, so for the axial stiffness looks okay, right? bending stiffness 12 6 4 minus 6 2 minus 12 6 6 2 6 4. What if we make it 0.5 times pi? Oh, pi over 2. Why is it? Oh, okay, that is a small number, right? 12 is the x. Okay, makes sense. 0 is the y. Okay, 12 minus 6 and then minus 12. Make it like this. This will be better. Minus. Okay. 12 6 minus 12 and 6. Okay, and 6 4 minus 6 2 minus 12 minus 6 12 6 6 2 minus 6 4. Great. Axial stiffness here 1 minus 1, which is in y direction, and then minus 1 and plus 1. Okay, looks good. The thing is that we have that very small number here, but it shows up, it doesn't show the 0. Okay, so it seems to work correctly. Come back to here. We need to plug in. So in order to plug in, for now, the matrix that we have is a 6 by 6. So for this 6 by 6, you have again 4 zones. Each zones just depend on the corresponding node. Alright, start node, end node, start node, ending node. Okay, but each of them has a 3 by 3 sub block. So previously for the truss it was like this. So it's changed from truss problem to planar frame problem. You have 3 DOF. That means for each node you have the 3 by 3. Okay, sets like this. So our job is nothing to do, well, the J 1 to 2, K 1 to 2, that does not change, but here will be the major change. Okay, so K6 3 minus 1 turns out to be minus 2, 3 and minus 2, minus 2, 3, minus 2, 3, 3J minus 2, 3K minus 2. Okay, this is the 1 1. 1 1 means, yeah, this is also 1 1, right, of that block. So we are talking about 1 1 of each block. Yeah, I copied this and then I've got to do the 1 2. I've got to do the 1 3. So for the 1 2, 1, the first in, where is it? 1 2 we change the second index, and 1 3 also we change the second index. Done. Right, for 1 minus 2 minus 2 minus 2 minus 2 minus 2 minus 2 minus 2, we change just the this which is this column, this column, this column. All right. And I will delete this and I'll copy all of this and put them here and put them here as well for another time. So you just don't want to leave any line blank. It could be dangerous in my viewpoint for the program. So 2 1, 2 2, and 2 3, and then we make it 3 1, 3 2, and 3 3. So we done with 1. Okay. For number 2, 2 1, this has been adjusted for the index 1 for the column already, minus 2, and for 2 minus 1, and for 3 minus 0. So we have to just change this minus 1 minus 1 minus 1. Here is minus 1 minus 1 and minus 1. This is minus 2, minus 1 is here. Okay, so minus 1 minus 1, and then minus 1 minus 1 and minus 1. Whereas this one we remove minus 2, we remove minus 2, and okay, great, we're done. Now the plugging in routine, which takes care of all 9 entries, is gonna work. Start with this zone and then move to this zone as the K changes from 1 to 2. Once done, then the J will change from 1 to 2 and K change to 1, so it comes down to here for 9 times, and then the last one to 2 9 times. So turns out we have how many? 36. When you work on other sort of element like 2D plane element, you might have 3 nodes, you have 4 nodes. If you have 3 or 4 nodes, then the block operation like this will not just range from J equals to 1 to 2. Okay, it's gonna range like J from 1 to 3 or 1 to 4. So you have 4 sub-blocks and 4 sub-blocks in each direction. The more node number you have, the more sub-blocks you have. Alright, so here we are good now. And then we modify the original system array for boundary conditions. Okay, something has to be fixed, like 2 to change to 3, 2 to 3. This is very dangerous. When things looks very easy like this, just change 2 to 3, 2 to 3, and then when the bug is there, it is so difficult to find the bug because you just go, oh, that looks okay. But we'll see. Keep the finger crossed. 2 to 3. 3 times the number of node. 3 times the number of node. Minus boundary condition I, 2. Okay, that's the index in boundary conditions. Okay, fine. Minus 1, minus 1. Okay. Guess it will work. So I think we are good up to here. Yeah. Then displacement, we just plug in the force, nodal point force. We have not incorporated the fixed end reaction, but maybe